Part 4 of 5. Features and Challenges in Quantum Computing. We start with a comparison of gate-based versus adiabatic quantum computing and continue with an overview of the current state of the quantum computing industry and future predictions. Gate-based quantum computing. Definition. Gate-based quantum computing is a type of quantum computing that uses a sequence of quantum gates to manipulate the state of qubits. Model. The quantum circuit model, where quantum gates are applied to qubits in a specific order, is the basis of gate-based quantum computing. Control. In gate-based quantum computing, precise control of individual qubits and quantum gates is necessary for the correct operation of the quantum algorithm. Adiabatic quantum computing. This segment covers the definition, principle, and control. Definition. Adiabatic quantum computing is a type of quantum computing that evolves a quantum system from an initial simple state to a final complex state to solve a problem. Adiabatic quantum computing is a quantum computing paradigm that involves slowly evolving a quantum system from a simple initial state to a final state that encodes the solution to a computational problem. This evolution is governed by a time-dependent Hamiltonian, which describes the energy landscape of the system. The key idea behind adiabatic quantum computing is to ensure that the system stays in its ground state throughout the evolution, so that the final state encodes the solution to the problem. In physics, Hamiltonian represents the total energy of a system, including both potential and kinetic energy. To achieve this, the Hamiltonian is gradually changed from an initial, easy-to-solve, problem to a final, hard-to-solve problem that encodes the solution to the original problem. During this evolution, the system follows a trajectory in its energy landscape, which can be thought of as a series of valleys and ridges. The goal is to follow a path that stays close to the ground state at all times, so that the system remains in the ground state and encodes the solution to the problem. Principle. Adiabatic quantum computing is based on the adiabatic theorem, which states that if a quantum system evolves slowly enough, it will remain in its ground state and therefore represent the solution to the problem. Evolution. In adiabatic quantum computing, the problem is encoded into the energy landscape of a quantum system, and the system evolves slowly from an initial simple state to the ground state of the final problem Hamiltonian. Control. In adiabatic quantum computing, less precise control of individual qubits is necessary, as the evolution of the system is determined by the energy landscape. Comparison. (1) Control. Gate-based quantum computing requires precise control of individual qubits and quantum gates, while adiabatic quantum computing requires less precise control. 2. Flexibility. Gate-based quantum computing is more flexible than adiabatic quantum computing, as it allows for the application of different quantum algorithms to solve different problems. 3. Scalability. The scalability of gate-based and adiabatic quantum computing is an open question, and further research is needed to determine the advantages and disadvantages of each approach for large-scale quantum computing. Explanation of quantum supremacy. Definition. Quantum supremacy refers to the point where a quantum computer can perform a computation that is infeasible for any classical computer. Quantum supremacy is a term used to describe the ability of a quantum computer to solve a problem that is intractable for classical computers. Specifically, it refers to the ability of a quantum computer to perform a calculation that would take an impractically long time on even the most powerful classical supercomputers. This milestone is achieved when a quantum computer can perform a well-defined computational task faster than any known classical algorithm. The concept of quantum supremacy is important because it represents a key step toward the realization of practical quantum computers that can solve complex problems that are beyond the capabilities of classical computers. Significance. Achieving quantum supremacy is a major milestone in the development of quantum computing, as it demonstrates the potential of quantum computers to perform tasks that classical computers cannot. Proof. Demonstrating quantum supremacy requires the execution of a well-defined quantum algorithm that solves a problem with a high degree of certainty and a large enough number of qubits to make the computation infeasible for any classical computer. Limitations. It is important to note that quantum supremacy does not necessarily mean that quantum computers are superior to classical computers for all tasks, only for specific problems that can be solved using quantum algorithms. In the next segment, we take a look at the current state of quantum computing and predict its future. Current state of the quantum computing industry. Advancements. The quantum computing industry has made significant advancements in recent years, including the development of new hardware technologies, the creation of more efficient algorithms, and the expansion of applications for quantum computing. Companies. A number of companies, including IBM, Google, Microsoft, Intel, and Alibaba, are investing in the development of quantum computing technologies and applications. Applications. The current state of the quantum computing industry is characterized by a growing interest in quantum computing applications, particularly in cryptography, finance, and chemistry. Cryptography. Quantum computers have the potential to break many of the encryption schemes that currently protect sensitive information, such as financial transactions and military communications. However, quantum cryptography also offers new and more secure methods of encryption that rely on the principles of quantum mechanics. For example, quantum key distribution, QKD, allows two parties to securely share cryptographic keys by sending entangled photons over a quantum channel. QKD offers a level of security that is provably unbreakable, even by a quantum computer. Finance. One potential application of quantum computing in finance is to optimize investment portfolios. Modern portfolio theory involves analyzing large datasets to identify the optimal mix of investments that maximizes returns while minimizing risk. Quantum computers could potentially perform these calculations much faster than classical computers, enabling portfolio managers to make more informed investment decisions. Quantum computers could also be used to simulate complex financial systems, such as the global economy or the stock market, to better understand their behavior and predict future trends. Chemistry. Quantum computing has the potential to revolutionize the field of computational chemistry by enabling researchers to simulate the behavior of molecules and materials more accurately and efficiently than classical computers. This could help researchers design new drugs, catalysts, and materials with specific properties. For example, quantum computers could be used to simulate the behavior of enzymes, which are complex molecular machines that play a critical role in many biological processes. This could lead to the development of new drugs that target specific enzymes and improve the treatment of diseases. Limitation. Despite the progress made in the field, the quantum computing industry faces significant challenges, including the development of large-scale quantum computers, the improvement of quantum algorithms, and the creation of robust quantum error correction protocols. Future predictions. Development. It is widely predicted that the quantum computing industry will continue to grow and develop in the coming years, with increasing investment, research, and commercial interest. Applications. The potential applications of quantum computing are expected to expand, with quantum computers being applied to solve a growing number of problems in fields such as cryptography, finance, chemistry, and machine learning. Hardware. the development of new quantum hardware technologies, such as superconducting qubits and trapped ion qubits, is expected to continue, and the scalability of these technologies will likely be a major focus in the coming years. Algorithms. The improvement of quantum algorithms is also expected to be a major area of research and development, with a focus on creating more efficient and reliable quantum algorithms for a wider range of problems. Discussion on ethical and societal implications of quantum computing. Security. One of the most significant ethical and societal implications of quantum computing is its impact on security and privacy. Quantum computers have the potential to break many of the cryptographic systems that are currently in use, which could have serious consequences for individuals and organizations. Bias. Another ethical consideration is the potential for bias in quantum algorithms and the impact this could have on decision-making processes. Job displacement. The development of quantum computing technologies has the potential to automate many jobs, which could have a significant impact on employment and the labor market. Accessibility. Access to quantum computing technologies is also an ethical concern, as the concentration of knowledge and resources in a few organizations could lead to unequal access to these technologies. Regulation. The development of quantum computing technologies is likely to raise new questions about regulation, particularly with regard to privacy, security, and the ethical use of these technologies. In conclusion, the development of quantum computing technologies has the potential to bring about significant advances in many fields, but it also raises important ethical and societal questions that must be considered. Thanks for watching Part 4 of 5 of Introduction to Quantum Computing.